As you mentioned, I'm Marko Rekic from HOPS, and today Krešimir and I will present some of our real-time applications that are used in the power system operation. At the beginning, this short agenda. The first thing we will introduce something about HOPS. Then the topic that I present is the wide area monitoring, especially wide area monitoring in the control room. And then Krešimir will talk about dynamic thermal rating and weather system in the HOPS. So Croatia is somewhere in the central and southeast Europe on the coast of the Adriatic Sea. You can see here on the map of the Europe and on the world map. And here in the middle, you can see our transmission network. We operate around around 180 substations, and what that is important, we operate with 110, 220, and 400 kV. So let's begin with the one topic. Synchrophaser application in HOPS. Here we get the scheme of the one system in the HOPS. Basically, we have around 60 or 70 PMUs installed in our network. You can see increase of those number in the last few years. Also, criteria for installation is tie lines, high voltage internal lines, points of connection with power plants, and some measurement for some network lines. PMU is the network measurement. We exchange synchrophaser data with TSO community, and we operate with two PDCs, phaser data concentrators. One is developed by our team in HOPS. It's called SynchroShield, and another is a commercial application, Wamster PDC. During the presentation, I'll try to explain which is used for what. And one important thing for today's presentation is that one system is with IC, one with our SCADA system. So basically, there's some algorithms I divided in groups. First group is real-time application, the scope of today's presentation. One is planning. Let's action function of one function. This all you heard today, but we'll go with my slide. And the that's something I won't talk about it today, but you can read it. We have overcurrent differential distance and fault locator on transmission line. Also, something about fault locator is always in the presentation because it's very useful. We'll see you later. So once in the control room, there is many aspects why we should use WAMPs in the control room. Also, there is many technical and non-technical, let's say, issues for implementing this this system in the control room. For example, when we talk about technical issues, we can say that we have some problem about communication network or exchanging data between some TSO or different IT policies between TSOs. Some SCADA system or EMS system are not suited for integration of the WAMP system, and also we have non-technical issues such as operator acceptance. The most, I would say, missing clearly defined countermeasures or action what operator should do after some event. Maybe usability of wide area monitoring algorithms and so on. So here's some present approach of how to implement WAMP in the control room. So if you have synchrophysical measurement, phase data concentrator, and some algorithms that are developed on the PDC, you need to extract this information and send those information to the operator in control room. But important thing that when you send those information in the control room, this information should consist of the clear action or countermeasure what operator should do. That's very hard to implement, but on our example, we see that if we put one system as a new system in the control room, they already have it, but to use the new system as it is, it's very hard because in control room they already have a lot of system, a lot of monitors, and each new monitor is a new problem. So basically, the idea is to implement with some existing systems, such as SCADA or any other system that is used in control room. And when you get some information, okay, I have some event, okay, is clear action or no, operators always should have an option to connect to the WAMP system and see more detailed situation. So that's the situation in our control room. Now we go with some graphics. Here just information of PDC views in our system. This is the commercial one-star PDC, some graph trends also here. Here's our development of SynchroShield. We can see angle difference monitoring, some unbalanced operation monitoring, graphical angle difference monitoring, some graph trends, and so on. And here we go with some SCADA views of the WAMP system. What we can see, this is the picture from our video wall in the control room, and this is part of the SCADA system that we can see counter coloring of the frequency. What is here important, how to get counter coloring of the frequency. If you put counter coloring of the frequency of the SCADA traditional measurement of the frequency, you will not get such precise amount of frequency or value of frequency, because you have some dead bands, you have some cycle period of receiving this frequency. But if you put PMU measurement of the frequency, then you'll have exact value of the frequency and no dead bands or so on. So if, for example, some island occurred in the network, you can see where is border or which part of the. Practically, this is the simulation of the January 8th in our system, and we can see one part of the island and the other part of the island. It can be useful, but what we talk also today, these all algorithms and applications are developed after some events, so such as this all what I'm talking today. Also, here we have some graphic in our SCADA system that is angle difference monitoring. As I already say, Walter, it's copy design of the SwissGrid web page. It's pretty simple. You got one reference point, and you got much point however you want, and you monitor angle difference. This monitoring of angle difference is practically the only one stability real-time monitoring, because you can see angle difference represent it is the answer to the active power flow between 2 points, and we already talked about warnings and alarms on this value of angle difference, but it's very hard to say okay, from point this and this, put the alarm to 50 degrees, and between point this and this, put to, let's say, 65 degrees or something, because you need to monitor in the high load situation, low load situation, during summer, during winter, maybe during years, I don't know, and find that angle difference behavior pattern and say, okay, this is critical, this is non-critical, and then you can put warnings. This is the one algorithm that do not have the clear action. An operator see warning of the high angle difference, they don't know, there is no clear action, but it is information that he needs to, let's say, keep eye on the system and see if there is any transmission line that can be turned on and to lower that angle difference or something like that. Also, here is the 1 hour, last hour of the angle difference graph that you can see. Also, if some disturbance is occurring, you can see by color on location where it's happened. Also on this tab, you can see the frequency. Frequency, I don't have it here, but it's when it's everything fine, it's only one line, and you can see. But when island is occur, you can see 2 or 3 lines, or how many islands are there. This is one graphic of, let's say, ambulance operation or broken conductor detection, where you can see the percentage of ambulance operation. In our system, we already have warnings with this system that also represent that broken conductor or something like that. But I'll say something more about it on the next slides. Also, that we have been done, it's integration of the one system with the AGC system, or automatic generation control, because we install, and we are currently in the process of installation, PMUs on our tie lines, because we have very large, say, fluctuation of active power on the tie lines in the short time. And what we have done here, we do integration of active power on the tie lines in the 2-second period. That's period of AGC, and we send that value of active power to the AGC. Practically, when you do integration, you are very close to the electricity meter of this power line, because you do, with the integration, you do energy transfer of this power line. And what we find out that when we use PMU measurement in such way, after all analysis, the small deviation is by PMU measurement, and compare it with the SCADA measurement or something like that. Also, one integration of the WAMP system with the AGC is island detection. It's a PMU based application. So when island is occurred, we send the indication to the AGC system, and then AGC system is going to stop mode, maybe not stop mode, maybe it's island mode, but Krešimir is our AGC expert. So if you have any questions about this AGC side, you can ask him later. And then each unit, or including AGC, start regulated active power by frequency. So if frequency is below 50 Hertz, then we'll raise the power. If higher than 50 Hertz, then we'll lower the power. Also, one real-time application that I mentioned before is broken conductor detection. We use symmetric components of the voltage and current for detection. And the important thing is say that this work very precise when PMU is installed on the power line. When PMU something is in the close to the power line with broken conductor, we can see raising of unbalanced operation close to this PMU. So it can be also warning and it can be alarm. I don't want to talk long about it. Also, what I mentioned, some let's say protective function is the fault locator that is very useful to us because on our 400 kV power line we have let's say disturbance few times a month, and fault locator on the relay protection was not precise, and they didn't find where physically is that problem. But when we put those power line under this fault locator monitoring, after first event, we get fault location, and people from department of the overhead lines go to this power line in the terrain and find exactly the place of fault. One last slide from my side is just to put one possibility of the one system in the planning and monitoring is the monitoring of the frequency containment reserve, where you can exactly plot. We have a system for automatic monitoring, and also you extract those data. When you plot frequency active power diagram, you can see the slope that practically represent the primary regulator characteristic. You can read megawatt per hertz and say this generator properly or properly. So I will finish now part of the presentation and continue with this part. If you have any, you can ask after presentation.
Introduction of questionnaire. I hope now it's working better acoustically. Krešimir has graduated in electrical engineering with the University of Zagreb in Croatia. Then he joined the Croatian transmission system operator for 13 years ago.
Yes.
And you are now of the process in many task force and working groups in those mentioned here, and you are representing in like synchro Parcross, exactly. Please go ahead.
Thank you. Now something but connected with those presentations of from today. So as Asya already mentioned, weather is, let's say, really important, and our lives and also power grid is affected by the weather outside. So at HOPS, we decided to make our own weather system. So it is based on GFS model. You probably all heard from its American Global Forecasting Model. So we grab input data from them 4 times a day. Input resolution is 27 by 27 kilometers. So we do calculations for 7 hours, and the result is grid weather data for the Croatia and surrounding countries for all the relevant weather parameters for 72 hours in advance. So we have 1 hour, let's say, resolution for 72 hour in advance for currently more than 500 locations, but we can export the grid, and but it's huge amount of data. So one calculation has more than 20 gigabytes of data, but nowadays it's popular. You probably heard about data lake and those kind of technologies. So we will implement that and save the grid forecast data. So besides the weather predictions, we also have weather measurements. So we have two types of weather stations. The ones that are installed in power stations are it's around 55 weather stations across the country. And we also have 15 weather stations. You will see later on the lines that are equipped with DLR. So it's good to have also weather stations on those kind of lines. So, but besides DLR system, weather predictions and measurements are also used for losses prediction in the network and renewables for the production of the renewables. So what we here, the way the most usual is that the weather forecast tool set. So it's pressure, it's wind speed, different from the ground. Currently, we have up to 100 meters, but it's user configurable, and it is trend that wind power plants are now getting higher and higher. So we will probably in next few years put even 120 and 140. Wind gust, wind direction, and the different height and temperature, radiation for the forecast of the production of our cloudiness. That is interesting also with radar reflection and the type of rain and type of participation and of rain. We also calculate based on these values if there is a chance of rain. That's if it's chance that we have ice and rain, we will also have it here as a result. And on the right side, you can see the values that we measure from our weather stations. So it's practically everything what we predict, we also can measure. Besides of this weather system in HOPS, we also have a lightning location system installed in the operator room. So here you can see on the left side, these are the locations in power system in transformer stations. So we covered all the Croatian region. And on the right side, you will see later on, we have 4 different 220 lines in this region. So we put also weather stations on the line. And just some details regarding the weather stations. So in transformer stations, all the data is sent each minute to the control room. And on the line, we have measures each 5 seconds, I think, and they send it over internet to the control room, and then we aggregate the data in 1 minute. So it's just simplified graph how the system looks. So we collect the GFS data over internet. We put it on 2 different servers. We'll calculate for 7 hours, and the results are saved into the database. Also, the data from weather stations and power line and from the transformer stations is sent through the network to the system. the end user has a web GUI application, so he can visually look into the data and compare. So here you can see the example of the wind speed prediction. The dark green one is actual measurement from the same location as the light green color is prediction. So you can see that those two follow each other pretty well. So the next slides are about the DTR system in HOPS. So the pre-requirement for the system that we chosen was the weather data. Without it, our system wouldn't work. So we have two types of, let's say, DTR systems. So the ones that are based on the actual measurements, and the one that we used, and it is installed on within SynchroGrid project, is based on the weather data. So the input is weather data and terrain profile. Project was started in 2018. From 2020, it is working, and we have the data in control room. So the pre-requirement also was detailed tower data. So the height and type of towers, and of course the line data needed to be input in the system. Some details about the DTR limit. So it is calculated every each minute, and we have forecast for the limits for the 3 hours in advance. So the result each minute is used also by EMS and the SCADA functions in control room. So I already said, but you will see it also on the next slide. So we equipped 4 220 kV lines with the Sumo DTR system. And also, because it is, let's say, new technology for us, we also implemented, and as a part of FARTRAS project, we implemented 2 other different technologies on the same line. So we had a chance to, let's say, compare the results and to check if the software-based solution is as good as, let's say, that we measure DTR or temperature on the line. So I already said that we equipped those 4 lines with the DTR solution. It is because the most of the production and wind power plants are here at the south, and the most of the consumption is at the north. So that's why those 4 lines were important as a corridor for power evacuation from the south. Here you can see the blue screen. You can see, sorry, the black screen. You can see the SCADA view from the operator point of view. So he has a chance to, let's say, turn off the use of the DTR system, and he has the values, the current values of the loading of the lines, the DTR loadings, and some other details about the limits of those 2 lines, or those 4 lines. Here, it's other interesting view that the operator can use. So he has a 4-quadrant diagram. In the first 2 parts, this line in the middle is current time. So he can see previous 3 hours of DTR limit, the forecast of DTR limit for the next 3 hours, and we have 4 of those because this is n-0 state, and this is n-1 state. So in case of for this line, the worst failure for that line would be the loss of this line. So you can see all that on the screen, and the warning if there is, let's say, high wind icing on the line or something like that. This is just the, let's say, logical screen and technical details how the system looks like. So there are many computers that, let's say, calculate limits, store the data, communicate with the other systems, and so on. Just some details about those two other systems that were mentioned in ParkCross project. So they are sensor-based. So the sensor is installed for the OTLM system on the line. Over here we have two, but one is enough. This was one project where we wanted to to look the loadings on the tower with two sensors, because this sensor also measures the angle of the line. But for this DTR system, it's okay that you have only one. So it is powered by the conductor, by the current that goes through the conductor, and it sends the data over GSM communication into the center. And if you use also weather stations together with the OTLM system, then you can have also DTR limits. But if you use only the sensor, then you only have the temperature of the line. And the other system it's installed on the tower here, and it has a LiDAR sensor, and it measures the distance from the line. So if line is more, let's say, hot, then it will be, the seg will be bigger and the line will be closer to the tower. So, and they have it, the data is sent to the line vision center, and they calculate the DTR limit, and we download the data by the API or internet. Sensor is powered by solar power. Someone is interesting. So here is the comparison of those three systems. So the previous software one based is in orange, and the OTLM is blue, and gray is line vision. So you can see the data is from the December 2021, and you can see that let's say patterns are following each other. So you won't have the same temperature from those three systems because they work differently, but the software one is good enough, and let's say that he is more on the safe, gives higher temperature, so it means that the DTR limit is lower, but you are on the safe side with the operating of the line. Here is the comparison for the 2021 year for one line. So the orange is the statical rating of that line. The gray is the actual loading of the line. And the blue one is DTR limit. So you can see that the most of the time during the year, you have a lot higher limit than the statical one. Of course, it is because that line is made, or let's say static limit is produced or made for the summer, where you have 40 degrees outside and really slow wind, but that is not the case for most of the time. And I think the last slide here is just for those four lines. You can see how, let's say in the percentage, you can see that more than 90% of the time, the DTR limit is higher than the statical one. That is all from my side. So please